A project sponsored through DRDO, which is for an object detection on runways. And LiDAR and these type of technologies we are working upon.
Myself, Ajay Vikram Singh. I'm also from AIT department, dealing with IoT and trust management issues, and heading a Cisco Academy in Amity University. People who are on also ask other people to join.
Hello, sir. Good afternoon. I'm Dr. Avshish Kumar, working in AIERS, Amity Institute for Advanced Research Studies. My research field, I'm basically working on a different type of sensors, optical sensors, biosensors, and gas sensors particularly. So I think few minutes back you were there in the department, so you have seen that facilities we have. Thank you, sir.
Good afternoon. My name is Avinash Chauhan. I'm working in Founder President Office, FSTIA, and we are working as a research facilitator in the university across the campuses within India and abroad. So we look after the research facilitation, like funded projects and all allied corporate alliances, academic alliances. We take care of all these activities from our department. Thank you.
Welcome, sir, to Amity University. This is Isha Sood, working in the Founder President Office at Amity Foundation for Science, Technology, Innovation Alliances. As the name specifies, that we look after the alliances between the different organizations at national and at international level, be it academia, be it industry. We look after and facilitate the same. Thank you.
I am Manu Mehra. I'm working in the field of electronics and communication, but basically it's front end and back end VLSI. So that also includes digital CMOS. So I'm working towards the digital domain. Yeah. Hi, Dr. Seema. Yes. Hi, Dr. Seema Rawat. I'm from IT, BTech IT, MIT School of Engineering. I already completed one project which is related to entrepreneurship. PMUI Yojana was a portal, and the project name was Udemita. Now I'm working with the AI domain. Currently, I'm working with the GAN model and Llama this time.
Good afternoon, all. I'm Dr. Neha Tyagi. I am basically related from computer science and engineering background, and I'm working on artificial intelligence and machine learning projects related to the healthcare. And in healthcare, right now I'm working related to the neuro diseases like psycho diseases. It's related to the narcissistic personality and the BPD personality disorders. So this is my area. Thank you.
I'm VK Jain. I'm VK Jain. I'm at Institute of Advanced Research Materials and Devices. And it was nice that today he has visited our institute. We have discussed many things. As far as ISC is concerned, I think I have visited more than a very large number, more than 50 times. Sometimes in many projects like this MEMS technology we have started in the country from ISC Bangalore, and recently it has completed about 25 years, this one. So there was a big function. Then he has a project also recently in Netra. This is a nanotechnology project from Ministry of Information. For last 5 years I was in that committee also, so we have gone many times to their institute. It's nice if we can do some collaborative work. They have a fantastic facilities, nano center, nowhere in the country you can compare anywhere in the abroad. And they are giving facilities and times you can go, you can work there. It is not chargeable. You can just apply, they will provide you this facility. So thank you very much.
Good afternoon, sir. Good afternoon. I'm Anup Shukla from MIT Institute of Applied Sciences, and I work on ferroelectric materials, piezoelectric materials and their applications. So our group actually working in two areas. One is the development of IR sensor using the pyroelectric material. So earlier we had developed the IR sensor material for intruder detection. A novel material was developed in our lab showing the maximum pyroelectric coefficient reported at that time. So for 1841 microcoulomb per centimeter square Kelvin at room temperature. So it was, I think, largest value at that time we exhibited. And thereafter, we took the another project from ARDB DRDO to develop the piezoelectric ceramic material for acoustic emission sensor applications. We have, huh? Yes, he was from Varanasi. I did my PhD from Allahabad. He did under Dr. Dhananjay Pandey. He was the student of Professor Dhananjay Pandey. So he is doing a lot of work on neutron diffraction and XRD. So, yeah, he's a wonderful worker.
Number of papers in Nature. Nature materials, advanced materials.
So thereafter we completed and transferred the know-how to the DMRL also for batch production of the ceramic material for their applications. And recently I have got another project from the ER and IPR DRDO for development of IR sensor for fire detection and suppression system. So this system has to be used particularly in the areas where explosives are kept and also in the army tanks, and we want to diagnose the fire before in the smoldering phase only, because once the fire catches, then it is almost impossible to stop that fire. So in the pre-stage, we want to diagnose and we want to check whether the fire is catching, and then we took the necessary steps so that fire can be stopped. So that's what we are looking at. Thank you.
So Anup Shukla is our materials man from
Hello,
the
sir.
Amity Institute of Applied Sciences. Yeah.
Hello,
Harish.
sir. Thank you very much for inviting me here to listen Professor Bhagwati Prasad. So I did my PhD in India, and the material was multiferroic material. So I am somehow related with the spintronics and magnetism. And then I have been focusing mainly on the hydrogen research for last 6 to 8 years. So I recently joined here as a Ramanujan faculty fellow. So the main focus will be scalable hydrogen production. And then we are also contributing in establishing the Center of Excellence here in Amity University. So that is our ultimate target. And in the same line, we are also initiating the basically integration of spintronics system with the hydrogen research. So especially the sensor and also hydrogen storage. And that is why I would like to hear from you as well. And that is why I'm here. Thank you very much.
Yes, can you?
Started actually about the tape casting. So piezoelectric ceramic tapes. So we have started working on that. We made the slurry, even cast the tape also. Following certain, we are having some problem with the sintering part, but hope to to eradicate all those problems in next few months. So we will be able to develop the piezoelectric ceramic tapes for multi-layer actuator applications also.
Can we also, Basant, we are joined by head of the mechanical engineering department. You met Basant, yeah.
We know him very well from so good afternoon all of you. So good afternoon. We know him from Hall 8 in IIT Kanpur. That time he did the masters and I was the PhD student. So sir, we have also common friends, and this morning he visited my lab and I explained whatever I'm working all these things. So I'm here heading the Department of Mechanical Engineering. So like I have a 30 faculty members. Few faculty members are working on a material, like I'm working in a cooling systems, that is a part of material also. We people also be a part of the hydrogen mission, where we have to be a use the hydrogen as a automobile sectors. This area we people are working. Like in my faculty, most of the faculty in material, they are working on a composite, metal composites, and they also working on some organic composites, kind of these things. And we have many facilities, like we have a plasma sputting and plasma coating facilities. We have a CVD chemical vapor deposition systems. we have a contact angle measurement device, and we have a high performance computing machine that you already see. And we people are using the open form as well as CFD and SIS, and we also developing our code. So these facilities we have under the department, and I'm very happy if you have a joint work with us. Yeah, thank you.
Let us introduce, let us introduce our Spintronics Materials Group Center. This is a very important group which he is interested.
Very
So
good afternoon to all of you.
expand on your expertise and what you are doing.
First of all, thank you, sir, for inviting us in this very interactive meeting. First of all, thank you, sir, for inviting us in this meeting, and thank you, Professor Bhagwati, for being here. Our group is at MIT Center for Spintronics Material. Basically, we are focusing on the structure as well as magnetic properties of ultra thin film, interface with heavy metals, interface with semiconductors, and non metallic materials like MgO and all. Here we have the sputtering where we can do DC as well as non-metallic substance sputtering. In this we can grow thickness gradient film as well as alloy films. Also, apart from this, we have an tabletop ion accelerator in which we can irradiate the samples with argon, helium, and nitrogen currently. And yes, there is a provision of extension of new gases. Apart from implantation, we are also irradiating the substrate for nanopatterning, so we can gradually grow the film as per the nanopattern substrate. Also, we have a mock measurement in which we do the longitudinal mock measurement. Also, we have in-house developed a facility in which we can do the mock with rotation. So we can have the anisotropical studies with angle dependent. Also, we have developed in-house here only an ultra high annealing facility up to the temperature 700 degrees Celsius, and it is having a very good vacuum of the order -8, and it is working well. Also, we have this plan to integrate a magnet in this so that during annealing we can anneal the samples in with the magnetic field in plane and out as well as the out of plane. Currently, device fabrication part is not in our hand because we are limited with this lithography. But we have a strong collaboration at Kyushu Institute of Technology in Japan. So, device fabrication parts were done with the help of the Professor Fukuma, who visited 3 months back here. Also, in Yamaguchi University, Professor Asada, he is well known for his deposition around the globe. Even the control of our 1 angstrom. Last year, he published that for Hitachi, he has deposited of 12 very fine 12 angstrom film, and we have the strong collaboration with Professor Asada. And Dr. Shubham work on FEPT based system, and I work in the amorphous alloys like COFB, CO2 FEL, and this.
Shubham, can you introduce yourself, your activities, your background?
Yes, sir. Good afternoon, sir. We work on thin films for memory device applications, and we want to extend it for neuromorphic computing as well as some device fabrication. As Dr. Hari said, we are integrating spintronics for hydrogen storage. So our future aim is that. And sir, sir, we expect we can collaborate with ISC because they have the device fabrication facility. So is there any possibility, sir?
Because we are lacking in device fabrication. Here we are having the basic structural characterization which we can relate with magnetic characterizations, and for we have to outsource this device verification characterizations. All the characterization we are having, even the neutron, we have the access of Bhag in Dhruva reactor. We did the PNR measurements, but device we are lacking. So in this direction, if you can help.
Yeah, just pass it on to the Shubha. Just give it to him. You have introduced. Who else? Where is Vaibhav? Vaibhav also. And Suchendra, you also introduced.
Good afternoon, sir. Myself, Dr. Vijay. I'm assistant professor in mechanical engineering. Our group is working on biocomposites. We are developing the composite material by the reinforcement of different natural resources and with biopolymer resins. And our main objective is to develop the composite material that have lightweight and high specific strength, so that we can use all these composite materials in different defense application, aerospace applications. And recently we are working in the field of interfacial strength of the composite material, because in so many previously developed composite we are seeing that there is a lack of interfacial adhesion. So we are trying to enhance that interfacial adhesion by the incorporation of different fillers, and we are exploring the natural fillers, because we are developing the natural fiber based composite materials, so that we are trying to explore the newer type of materials by which we can develop these composite materials. And we are working on mechanical strength, tribological properties, temperature, because nowadays defense have very potential application of tents, lightweight tents, that can sustain the temperature in minus degrees or positive degrees. So we are trying to develop these types of composite materials so that we can use these composite materials in real time applications. Thank you.
Thank you. Dr. Opisima.
Sir, good afternoon and welcome to the meeting. So we are basically Nanotechnology Institute, India first institute in nanotechnology, and we have the diverse background faculty from physics, from chemistry, engineering, biology, and we are working on the nanocomposite. We are working with the nanostructures. We are working with the semiconductor. We are working with the sensor, healthcare. We are working for energy sectors. So we have the different expertise. And the on average publication of the faculty is coming around 4 to 5 per year. So on average publication of the faculty. So generally we have the last year we have the 60 publication. This year I have to check. So and still we are the only institute in MIT who have granted the FIST grant twice. So for earlier we have granted of around 40 lakhs. This time we have granted the 2.2 crores. So
thank you, Dr. Sinha. And Dr. Vaibhav, introduce yourself. He is also in materials.
I'm a proud alumni of MIT
University
University.
of Nanotechnology.
I did my BTech and MTech from here in the field of nanotechnology. Post that, I did my PhD from Victoria University of Wellington in New Zealand in the School of Chemical and Physical Sciences. And I was working in an area related to you, sir. I was working on magnetoelectric nanostructures in the form of core shell nanostructures as well as nanofibers. And I was also working on one other project which was funded by the government itself. It was developing new magnetic materials for their application is wireless chargers for electric cars. So these were two projects I was working on, and we look forward to having you here and more research collaborations and listening to your talk, sir.
Dr. Suchendra.
Hello, welcome to MIT. So I'm Dr. Shuchandra Banerjee, Senior Scientific Officer here in ASTIF. So my research field is not directly related to you, but I also use CCD cameras, CMOS cameras, because my field is optics and photonics. So I develop several prototypes using optics and photonics, which are useful in defense, space, and healthcare sectors. I also develop several like automatic algorithms to detect like ophthalmic diseases. So, and yeah, thank you so much.
Thank you. Just pass it on to her. You have joined recently. Introduce yourself.
Okay. I'm Dr. Sakshi. I have joined MIT Institute of Information Technology. I have recently joined, and My field of work in my PhD was on handwritten mathematical expressions. So basically, I belong from pattern recognition field. I have worked with computer vision, machine learning, and artificial intelligence based models. And currently, I'm working as assistant professor there. That's it.
So, Dr. Bhagwati, you have seen the people who have been selected to attend have been handpicked to interact with you, to build in your consortium as an active member to contribute from Amity University. Let me give a background how Bhagwati landed here. Dr. Atul Chauhanji, our Chancellor and also President RBF, who RBF is the foundation, Ritanand Balved Education Foundation, which gives cover to all our Amity education group. So he is our president and also the Chancellor of Amity University, Uttar Pradesh, in addition to other universities. And we met him when we went to Bangalore just about a month ago. We were at the hotel in which an MOU was signed between Rice University and Amity University. And the main function was that they are establishing Rice University and Indian Institute of Science, Bangalore, an innovation center. So in that function, this MOU was signed by our Chancellor, Dr. Atul Chauhanji, and along with the President of Rice University, we signed this for collaboration. So at that function, we met this brilliant scientist, and then he interacted with our Chancellor for quite some time. So Chancellor was very fascinated because at the age of 37, 38, he has filed 40 patents, and that, out of which 35 are US patents. Only 5 are Indian patents. His H index is 20. So then he has also developed products and he has worked with great institutions like PhD from Cambridge, University of Cambridge. Then he has been to Max Planck. He has also been to University of California, Berkeley. He has worked there and also now in the Indian Institute of Science. So he has a great experience of these great institutions. Now what he is looking for, why he is here, is he expressed his desire to Chancellor that we would like to build a partnership between the materials engineering department of Indian Institute of Science, where he works, and he is also Infosys Young Scientist. That's a fellowship scheme, and he is an Infosys young fellow, and also so he's a very highly talented. So he expressed desire that I would like to partner with you, with Amity University, with us. So then he spoke to our Dr. Atul Chauhanji, the Chancellor. So then he asked me to coordinate this visit because I had the occasion of meeting him along with Chancellor at Amity, at the hotel there where we signed the MOU. So he went around in the morning, in the forenoon. He saw the beautiful facilities because I wanted him to get an exposure. First, what is the human resource available in his discipline? So you are the brilliant, talented guys. Where will you find such brilliant, committed, devoted, motivated scientists with such great accomplishment at your ages? So that is one. The second is we also wanted to display our strength in terms of research and development infrastructure available in his domain where he is looking at. This is the only university where you have a separate center for spintronics materials, and we have 3-4 people working in this area where you are interested. And then the next thing is we have the right ecosystem, right from the founder president, Dr. Ashok Chauhan, whom you see in that photograph, who himself is PhD in chemical engineering, and 28 years he worked in Germany, and then he became a non-European, the largest non-European investor in Germany when the reunion took place between East and West Germany. So he is completely driving the research and innovation in all Amity institutions. So on his behalf, I welcome you, and on behalf of everyone from Amity University, and on behalf of Chancellor, and who in fact asked me to invite you to show you around and build the partnership. Let me put the challenge what he is looking for, so that you people should now start thinking. See, now the computational capability and data handling is taking place not only in exponential way, logarithmic progression. If you look at the energy consumption from the computers, cloud computing, all the servers which are being used, and the AI facilities being used, 30% of energy is going to be consumed only in this computational job. It could be IoT, it could be AI, it could be data analytics. So we are going to consume that much energy. So now the challenge is, how do you optimize this energy consumption while not compromising on the speed of computing or the memory storage of computing? Memory storage, this is also important. So how do we do that? For which we need new materials, new architecture, new processes. And so this is what is the challenge. Now I want to, before his lecture, what is that he is looking for from us? So that this 30%, which is the expected predicted energy consumption for computing, can be optimized to maybe 20%, 15%. So this is the challenge. Now you start thinking in that direction before the lecture. Then he is looking for strong academic research partners. So he is considering Amity as one of the strong academic research partner, which will form in this consortium, where Rice University, where we have signed an MOU. So we already have a MOU connectivity with them. And then Indian Institute of Science, the director was there in that function, so we had a very close relationship with him. And in fact, we gave honorary doctorate to the director, current director, Indian Institute of Science. So we have everything available. So in this meeting, after you listen to the lecture and start giving thoughts and then mention, this is the area in which I will be able to contribute in this consortium, which we are like, for example, Indian Institute of Science, Rice University, and Amity University. If he is looking at other partners, we will ask him. So this is the biggest consortium, and so please keep that in mind when he is going to listen to his lecture. As I mentioned, that he is a very highly talented scientist, and he likes Amity, because having seen the profile, he told me during lunch, Amity has great experts as well as the facilities available. So their desire is there from him as well. So with this preamble, I invite Dr. Bhagwati Prasad. He has publication in Nature, which is more than 50, and then also Nature Materials, which is about 47 or so. The impact factor, I'm talking about impact factor. And he has a large number of publications in these advanced materials, nanoscale, and also he has publication in the other top journals which deals with spintronics, energy. So in all this area he has contributed. As I said, 45 US patents and 5 Indian patents, 50 patents he has. And so with this great strength, we like to look forward to work with him. So I would now invite Bhagwati Prasad to give his lecture, please. Give a big clap to him and welcome him for the lecture.
So yeah, thank you, Dr. Salva ji. I mean, you said a lot of things. I don't know how will I'll be able to justify this or not. And yeah, and also I thanks to your Chancellor, Dr. Chauhan ji, and we had a very nice, constructive, dynamic interactions in that meeting. And I found like he has this energy and eager to really make the difference.
Bhagwati, you speak to that mic. This is for recording. No, you speak to the other one. Yes.
Yeah, so I found the eager and energy enthusiasm that he has. He really want to make the difference, and not only in the university, Amity University, but in whole ecosystem in India and across the globe, and how Amity and overall how we as in India can contribute in the bigger picture of this technological world. So then I met with the Professor Ramamurthy Ramesh. I have worked with him, and he introduced me to Dr. Chauhan, and so that way we interacted. And then Professor Ramamurthy Ramesh told me, why don't you to have a further interactions with them and figure it out what like they came here, the University people, they came here and they were really got quite impressed with the facility infrastructure the Amit University have. And then we had some informal discussion, and there we thought that we should have more engagement with the Amity University and figure out how we can together make some consortium and do something together. So this is a kind of the first step to have some interactions, and how let's see how things evolve in the future. So looking forward for this dynamic interaction. Yeah. So with that, I would like to start my talk, and I was quite confused what to put in my presentation. In fact, just few minutes back, I was even editing it because I see people from very different backgrounds and different interests, and also this is a kind of institute where people are more maybe interested on the AI side, and particularly AI on the software side, which is not of my background. So it's really difficult to really make a presentation of that kind of diverse and expert audience. So let's see how I can put things together. So I'm talking about computing in the age of AI and IoT, and what are the challenges and beyond CMOS computing. You may see several logos here. That's because I have been so many these places, and so yeah. So yes, I did my MTech from IIT Kanpur, and there I met Basant, Dr. Basant. Yeah, we were sharing the same hostel actually. Yeah. So in fact, we have a few friends, common friends. Yeah. So after doing my MTech, where I worked on magnetic nanoparticles, which can be useful for the drug delivery applications and other purposes, but that background helped me to do something interesting in Tata Steel. So I worked in Tata Steel after my MTech in Jamshedpur. And so I'm basically, by training, I'm a physicist. I'm not the metallurgist, but I landed to Tata Steel without knowing what to do in Tata Steel. But I don't know why they even hired me. Okay, so when I went there, our director told that I don't know what you will do here because you don't know anything about the steel. So he asked me to figure out by yourselves what something new. I don't want you to do steel because people can do better than you in steel. So you figure out something else. Then while doing the induction program, I found that they use this steel, in the steel industry, they produce lots of these oxide fines, which is basically the waste product. So typically, some of you from the metallurgy background may appreciate this, that when this the thick slab of the steel or iron goes from hot roll mill to cold roll mill, before that you have to cool it down. Okay, and during that cooling, you do this with water, you form a thin layer of this oxide, and then they remove this by some acids, which is called the pickling process in a pickling plant, and that they produce tons and tons of this iron oxide. It's just Fe2O3, but it's a very small particles, like particles less than 100 nanometers, and they don't know what to use that, what to do with that. So since my background was in magnetic nanoparticles, I just explored that, and I found that we can basically use them for arsenic removal. And then we developed the technology. So we have 4 or 5 patents on that. We developed the technology with these fines. One can actually make the water purifier. It was one of the cheapest water purifier, which can not only remove the arsenic but all sort of heavy metals, other contaminants, and make the potable waters. And we also published a very beautiful paper on this desalination, which is like 10 plus impact factor. Besides that, I also come up with the idea. That time people are working on a thin film photovoltaics. Now the craze has little went down because this polycrystalline silicon has become quite cheap. But that time everybody was looking how we can make thin film photovoltaics. So that time we came up with the idea that why don't we coat steel with the photovoltaics. So some of you are working on the photovoltaics. That's why I'm saying this. So I had a collaboration with the many universities, IIT Kanpur, IIT Bombay, then Cochin University, then Warwick University, Delft University, 6-7 University. I spent a lot of money of Tata Steel on that, and we did a lot of great work also together. And so that was my another efforts. So I spent 3 years there, and then we were doing the field study. So this is the arsenic removal water purifier that we developed, and we installed those filters, those systems in some of the arsenic affected area of West Bengal. And we have done long field study, and after that we have developed those products. Okay, so after that, after spending 3 years in Tata Steel, then I joined PhD program in University of Cambridge. Okay, and there is completely different things I have started. Basically, I worked on spin tronic wave systems. Basically, we developed some sort of spin filters. No, not really. No, 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 no. So that was in the Tata Steel. Umapati was in Tata Steel. No, ISC is no, no, yeah, no, no. This is long back. I'm telling the story of 10 years back, 12 years, 15 years back, in fact. Yeah, so then I did PhD in Cambridge. There I worked on the some spintronic devices. So the main purpose was to make the spin filter. So the idea is that can you filter the spin of the electron? So electron may have up or down spin. So can you really block one spin direction of the electron and allow only other spin direction to go? So I'll talk a little bit about this today because I see that there are some audience who knows spintronics. Okay, then I spent some time in Max Planck Institute in Germany, Stuttgart, as a scientist. That was a kind of permanent position, but then we decided to move on. So there I developed something very different and crazy. This is with a Professor Jochen Menhard. If some of you know him, he liked to do something crazy. So though he works on oxide system, but he asked me to do something crazy to pattern the liquid, to pattern the water. Like you pattern solid state materials like semiconductor materials, thin film, you make capacitor transistors. So we pattern the water and we make some transistors with that. So today also a little bit I talk about this, which can be used for neuromorphic computing and some AI kind of applications. Then I joined University of California, Berkeley with Professor Ramamurthy Ramesh. Some of you might know him. He is the vice president of research at Rice University, and he is very well known figure in the field of spintronics and multiferroics. And
He visited here.
He visited here
2 months ago.
Exactly, he visited here, and we are having a very close connection. We are planning to have some startup together. So anyway, so I worked with him, and we had a team with the Intel, and we developed a completely new logic systems, which is called the magnetoelectric spin orbit logic, with the team from Intel. Yeah, so I'll also talk about this work today. Then I joined Western Digital. So Western Digital, this is a place where all sort of memory technology has been developed since the beginning. So it used to be IBM Research Center. Okay, so there were two contemporary things were happening. One is the logic, which is Fairchild Semiconductor was there, and then there's the IBM, which was mostly focused on that particular site, was focused on the memory development. So this is the same site now with the Western Digital. There I have developed, worked on novel RAM devices, non-volatile RAM, which is basically magnetoresistive random access memory, MRAM, and also some ferroelectric based memory, FTJ, ferroelectric tunnel junctions, and FERAM kind of things. Yeah, so we filed 40 patents, and almost all of them have been already granted. Yeah. Okay, so coming back to the today's world, present. So today I'm in the ISC Bangalore. This is my group. We work on the disruptive electronic materials and electronic devices. So why I put the disruptive word here? Because the electronic materials seems very cliche. So I put disruptive because it gives you some energy as well. So we work on all sort of interesting materials like electronic, magnetic, energy, 2D and quantum materials. And then we use the knobs of spintronics, iontronics, ferroelectrics, and magnetoelectrics. And eventually with that, we basically make nanoelectronic devices, AI, IoT hardware devices, neuromorphic and quantum computing systems. My one of the main focus is to develop the non-volatile memory technology and data storage technology. And also we are working on the sensors like magnetic and electronic sensors, biosensors, neuro sensors, and some virtual reality and augmented reality based sensors. This is what we work on. Okay, so this is our other ongoing work, because I see some of the people are from bit different backgrounds on electronics backgrounds. So I put this slide just few minutes back. So we also work on the ADFMR, acoustic driven ferromagnetic resonance based magnetic sensors. So what it can do, basically we use a piezoelectric substrate, and a piezoelectric substrate we create the surface acoustic waves. With the surface acoustic waves, if you put a ferromagnetic metal on the top of that here, you can basically create some sort of resonance, which is called the ferromagnetic resonance on that. And then this surface acoustic waves, you have this interdigited transducers here, and like input and output, and then you basically have input power from here and output power you can see here. And so if there is a resonance is happening, then this ferromagnetic materials can absorb that energy. Based on the energy, how much it has absorbed, you can basically do back calculations with some sort of simulation, and then you can know how much is the magnetic field presence in the surrounding if you have some field around. Yeah. So we have some system where we can actually cancel the background magnetic field, which is basically earth magnetic field, which is in the micro Tesla. So we are talking about measuring the femtotesla magnetic field, and this kind of magnetic sensors are useful for many biomedical applications like magnetic myography. For example, we use today the squid based system for this magnetic myography, which is quite expensive, which work at low temperature, cryogenic temperature. So we can actually develop that kind of sensitivity, but it's very small, tiny and very cheap. Like in terms of cost, very cheap, and you can put many of them and you can basically get the similar kind of sensitivity. Besides this, we are also working on various piezoelectric sensors. It's mostly me and Professor Rajiv Ranjan are working together, and he works on the more bulk systems, and I work on thin film. So we developing thin film of these piezoelectric materials and developing those sensors. We also making the phase shifters and microwave filters with basically having the tunability in the capacitance of those ferroelectric materials. You can tune their capacitance and you can use them for various filter applications. We also using this. We also making the ceramic supercapacitors, like ferroelectric based supercapacitors with very high energy density. Recently, we submitted one paper in Science based on that work. So which is under review, which is saws one of the highest energy density, like record energy density with these supercapacitors. So one of the supercapacitor that we are developing is unique because it's very sturdy. You can heat this to up to 400, 500 degrees centigrade. Nothing will happen. You can throw it from one building to the building because these are oxide ceramic based systems. So very sturdy. It can last for years and very good, property. Then also I'm working on the crossbar array of memory, like memory technology. Yeah. Okay, so these are some of the experimental facility that I developed in 3 years. So I just completed 3 years in ISC. So we have if some of you might know and some of you may be interested to use some of these facility in collaborations, we have a PLD, something called the pulse laser deposition technique, which you use for growing the high quality stoichiometric complex oxide and material systems. You can basically make the single crystal material without any defects, without any grain boundaries. You can make this kind of films. You can also make multi-layer structure, heterostructures, or different kind of materials. So you can basically create a new novel material system which doesn't exist in the bulk, but by doing this atomic engineering, you can have a novel material systems. We also having a sputtering, as the spintronics group saying here, they have some spintronics facility. So we also have a similar facility, the sputtering techniques. So here we have a cluster two chambers, and then there's a load lock. We have a total 10 guns. So all sort of metal, you say platinum, cobalt, iron, tefnoldy. These guys might understand what I'm talking about. Cobalt, iron, boron, whatever you say, we have all those things. We are depositing those. We are making multi-layers, PMA, SOT, spin orbit torque, spin transfer torque, voltage control, magnetic anisotropy, all sort of things we are doing. Also, we actually this RF systems, because they are, one is a DC chamber, other is a RF, so we can transfer the sample from one chamber to other chamber without breaking the vacuum. So that way, if you want to grow some spintronics stack on the top of multiferroics materials or ferroelectrics for some voltage control or a strain, apply some strain and modulate some restrictive property. So for that, we first grow these ferroelectric materials in this RF chamber. And then we can transfer from here to here, and that way we can grow the ferromagnetic metal on the top of that without breaking the vacuum. And also in this chamber you can go to very high temperature, up to 800, 900 degrees centigrade. So you can grow epitaxial film basically in situ, all in situ, no without breaking the vacuum. Yeah. So we now, you might appreciate, we are actually developing some magnetic skyrmions, okay, and then we are modeling those skyrmions with electric field through this means. Yeah, well, we saw some very interesting data with that. Okay, so we also have other PLD chambers and some sputting chamber with the 3 guns and RF sputting chamber. So a lot of things we do in this area, in this field, mostly thin films, but ferroelectric, ferromagnetic, multiferroics, all those things we deposit, and also sometimes complex oxide system as well. So within 3 years, we could develop. This is all facility within my control, but there are a lot of facility, as professor was saying, that we have a lot of other facilities in our institute. And Sense has a beautiful facility. Anyone can use that facility. We have a lithography. So I have been many places, Cambridge, like MIT, Stanford, UC Berkeley. I can say that the Sense facility that we have, the fabrication facility, is the best among all of that. In fact, the best all those facilities. The reason is that because we manpower is cheaper here, and that way we have a lot of people who can take care of the tool, and so our facility is always up. You rarely find the downtime of this tool. So all the time they are running. So this is a big problem. Though we can buy the tool, but maintaining the facility is the biggest problem. So that is really great thing in the sense. So all the time, all the facilities are available, and we have the state of art facilities. You can do TM. We have a also we have a, some microscopy centers. Actually, we have a 3 Titan in our institute, 2 to 3 Titans, and 5-6 TM, maybe 15 ACM, and 20 XRD machines in a whole institute. Okay, our department has a 3-4 XRD. So all sort of facilities we have to do whatever you want to do, and you can do all sort of transport measurement. We have a 2 E-beam lithography, 2-3 photolithography, reactive ion etching, whatever you need, we have all those facilities. Yeah. This is more. You can see the domain. You can also measure the POMH, basically loop, hysteresis loop, and this is both in plane, out of plane, both. So it's polar as well as the longitudinal. So the in plane field is a 6 kilo ostrich, out of plane is only 600 ostrich. Yeah, both. Yeah. I saw your MOOC facility, this yeah, office. I mean that room. Yeah, but I didn't go inside. Yeah. We can also do the polar part. It is very difficult to rotate the sample. Yeah, but we have a 2 different magnet here, both separate magnet for in plane, out of plane. Yeah. Oh, this simple Hall effect setup. Yeah. But quantum Hall is just measurement. So you can do low temperature measurement. So we have other system, this cry-free setup, where you can do low temperature like 1.5 Kelvin. 7 Tesla. 7 Tesla. 7 Tesla. Yeah. Yeah, we are now going to get PPMS soon. Maybe we also got the FIST grant so recently for the PPMS. So we are going to buy PPMS, and so with that we will have all those things as well. Yeah. Okay. So this is my group. You can see a lot of people, big population. Yeah, so I have around 15 to 20 people. It's a floating basically. Some people join and some leave, like in projects. So also I got some decent funding from my institute ISC and from several other funding agencies like CEPIPRA, STARS, ISRO, Tata Steel, and then there is a quantum centers we have in ISC. So they also give some funding, and I have some industry funding as well. Yeah. Okay, these are my collaborators, and I have been keep collaborating with the people, Ramesh and other people. Yeah. Okay, so this is our recent research work. So I have developed the ultra low power operating magnetoelectric memory devices. As we just told that we can actually switch the magnet with the electric field. For the very first time, we have demonstrated that you can switch the magnet with the energy. If you convert the energy, it comes around 10 autojoule basically. So the voltage, the corresponding voltage is around 200 millivolt. We just apply 200 millivolt. You can switch the magnet from one state to other state. Yeah. So then, so basically, this is a continuous study. We have done so many work to figure out these things. We published several articles on that, and then we also develop a new logic, which is called the MESO, magnetoelectric spin orbit. So he might be appreciate this. So there are 2 components. One is a magnetoelectric, where you switch the magnet with electric field, and there is a this spin orbit coupling, which is basically we are using inverse spin Hall effect, where we can convert the charge current to the spin current to the charge current. So basically, you can one way you convert charge current to the spin current, and then again spin current to charge current, and you can store the spin as your information. Okay, so that kind of new logic system we have developed, and recently we demonstrated this. So this paper, the one Nature, this 2024. So in that paper, if you are interested, you can go through this paper. We have clearly mentioned how it works, and we have shown the proof of concept devices on this. Yeah. Okay, so besides this, I have been working on the various flavor of the magnetoresistive memory devices, MRAM, which is spin orbit torque, spin transfer torque, voltage control, magnetic anisotropy, okay, and then voltage control of exchange coupling. So those kind of things we have been working on. Then all controlling anisotropy of the magnetic anisotropy, yeah, PMA, perpendicular magnetic anisotropy, yeah, yeah. Yeah, so basically you choose the stack, which is a PMA, perpendicular magnetic anisotropy. Then you have MGO barrier, then you apply the gate voltage and you modulate the basically interfacial anisotropy with that. Yeah. So also we made some this RKKY coupling stacks, okay, where we have a metal in between the two ferromagnet, and then we apply the electric field, and then we change their coupling from ferro to anti-ferro like that. So that paper recently published in Advanced Functional Materials. Yeah. Also, I'm working on the ferroelectric memories. So ferroelectric tunnel junction, ferroelectric RAM, also anti-ferroelectric tunnel junctions. So you can also use anti-ferroelectric property of these materials for computing applications. We also looking them for neuromorphic applications. And as I told, that spin filter devices where you can filter the spin of the electron, and that way you can generate the highly spin polarized current for some spintronics applications. We in collaborations also we have demonstrated the polar skyrmions. So far people are more familiar about the magnetic skyrmions, but the counterpart of this magnetic spin is the dipole, electric dipole. So can you also have that kind of skyrmionic structure? So that is what has been demonstrated, polar skyrmions. Also we worked a lot on interfacial electrostatic engineering, and then also I have worked on neuromorphic computing systems based on the pattern functional liquids. Okay. Yeah. Okay. So now let's coming back to a little bit on the general side. Okay. Otherwise it become a bit boring. So okay. So we like to work on the disruptive technology. What is a disruptive technology? Means sometime when I put the disruptive word, in my group name, in my department, people say don't use this word. It is not. It doesn't sound that good. But I said no. I want it to be sound something weird, and people should look into it. So many people even don't understand what is the meaning of disruptive. They think like I'm just going to create a big problem here. That's not actually. This is one way, positive way. It's correct. So basically, disruptive technology means you completely change the ecosystems. You bring up with a new idea. That new idea first will not be even appreciated. Okay, it may have a low quality use, then it will go to the medium quality use, then high quality, and one time it will basically surpass all of that, and you will be having a new technology. So for that, we need to have a novel ideas, novel thought process. So if we just recently I went to this MRS conference in US, so I go there quite often. I have invited talk there, which was in Boston. So I was invited in the science editorial this dinner party. I went there. I talked to the science this chief editor. Okay, and while he was a little bit drunk, so that time I discussed with him so that I know the truth, what he think about us. Okay. So otherwise they are very polite. They won't tell what they think, right? Yeah. So I told that, see, I submitted paper in science and you rejected without even reading it. And then when I submit the appeal letter and with a lot of big explanations, then you consider it. Why? He said, most of the things that come from India, that is what he's thinking, that is mostly repetitive. You don't do any new things. You basically add A and B together and just show something, and then that's how it goes. And that's actually the impression. It's maybe not true, but that's the impression. And he said that the same impression we used to have for Chinese, but now that's not true anymore. And they take all Chinese papers seriously. If Chinese is submitting paper in science, they will read it, they will think about it, whether it is useful or not, and then they will reject. But if something comes from India, they even don't read it. They just reject it. So that is the problem. So I think what is we probably need is also change the impression, that bring the noble ideas, not just to repeat what West is doing, but why don't we create our own way of thinking in noble ideas? So this is what the disruptive innovations and disruptive technologies. So I looked this some report, McKinsey report, and these are the some ongoing disruptive technology where people have been working. As we see, there are a lot of people from various departments here are working in these areas like mobile internet, automation of the knowledge, Internet of Things, IoT devices, cloud technologies, advanced robotics, and autonomous and near autonomous vehicles, and energy storage. Many of probably you are working on energy storage. 3D printing, it's also coming up with a very big way. In several group in ISCs are working on 3D printing nowadays actually. So that's another interesting area of research. And advanced materials. So DST has come up with a call with the advanced materials. I don't know any of or many of you might have submitted their proposal. Yeah. So then I heard that the DST is going to come a big call on the advanced materials. The aim is that to develop the COE, Center of Excellence on Advanced Materials, and that would be basically a big thrust on one particular area, and you develop the new novel materials and fundamental materials and yeah in house, and develop that kind of expertise in India. And also advanced oil and gas explorations and recovery and renewable energy. So these are the ongoing disruptive technology. But what is beyond that? This is the current ongoing. What we can think beyond this, like in future, what might be happening? Okay, so that's what I also find in the report, that wow, this is a really big thing. So potential of the 100 trillion market. So there's a huge opportunity here to how to, if we look into for the market wise, we can see that all these disruptive technology, if we can really bring some technology out of that, it create a big market for India and as well as for globe. Okay, other important, as I was talking to Dr. Salva Murthy sir. So see, I mean, education is important, but what I see that the education is becoming very, kind of routine practice now. We are not bringing any new novel innovations on that. So even what is happening is that is now kind of more of going toward the techie side, like you are using the augmented reality, virtual reality for the educations. So you are using the more technology to learn things faster. Okay, so that way the world is going. Instead of having the novel concept, novel thoughts, it's more of using the technology and learning those concepts. So question is coming in the mind now, that what would be the new future way of education? How will teach the students? What will they learn? Now what I found when I teach in ISC, I found that what is happening with the student now, that they are using chat GPT for every time, for everything, small things. Their thought process has been not developing well, because when you write, when you make some report, that time you use a brain, you think what is the right way of writing, your thought process develop with that, and that's missing. So I'm also a little bit wondering that where we use the technology for teaching, probably we lose this kind of thought process, this thinking. So that is probably is important, that how we can keep the right balance between these two. Okay, so we are also going the smart digital life, Internet of Things, okay, where we know that all these objects soon would be going to connected with the internets. And in fact, there's a very nice, probably I have that slide here, which might be in the latest. Yeah. So we may be having a very fancy offices, fancy homes and kitchens and all that, where all your objects, kitchen utensils are these appliances would be connected to the internet, and all will be automated. So that also would bring a new era of the life, how we live the life, and how we can use the technology for their purposes. Okay, so that's the more of the big jargon words. Now, toward the traditional things, if you look about the semiconductor industry, which is basically the backbone of all those things, is going toward the 1 trillion revenue path, and where India is now focusing a lot actually. Okay, so you can see that how semiconductor industry has come along. So till 1990 it was the era of the mainframe. Then till 2000, from then to till 2002, it was the era of the PC plus internet. We saw a lot of internet stuff has started, and then we were in the era of the mobility. Now we are in the era of the IoT and AI. So you can see that how the Nvidia stock is going up, because they are bringing the new innovations, they are giving the AI chip. Now Intel is no more is in a competition. They, in fact, their stock went down and they were kicked out from the Nasdaq because that's not, though they are making the chip, it's not useful anymore for that purpose, which is what market is looking for. So that's what also important, that today if we are doing something in the semiconductor, what is our goal, where we are looking for? Are we developing the technology which is in the which was in the market 10 years back, or are we looking something like what will happen 10 years down the line? And this is very competitive market, actually very competitive, dynamic and capital intensive. A lot of money is also required. So I think it's also required a lot of thought process that which direction we should go. Yeah. So many of you know about semiconductor chip. Like if you look your mobile phone, and there is a IC in your mobile phone, if you look, which have lots of billions of these transistors and capacitors, and that's how the single transistors look like. And basically the transistor that you use for the logic purpose, and with the gate voltage you can basically get on and off current, and that you use for this purpose. But when you develop this, when you manufacture them in industry, it is in a very different game altogether. Now if you see that a 300 millimeter silicon wafers, okay, that, and if you take the small area of that wafers, is 10 mm by 10 mm, okay, in that small area, if you see that there are so many interconnects and transistors, and in fact if you count that, in that small area, if you look, there are 60 miles of the wires which goes for the interconnects, okay, and then it has more than 10 billion transistors in that small area for the logic operations. So eventually that we see to in our hand, it is coming up after so much of the work, from materials to the final devices and the packaging and all that. Yeah. So this is where the semiconductor industry right now. Now, as we are going toward the semiconductor technology, we have to think about how we can really approach there. So question is that, is this the right game for us to play, or we should go beyond that? Because this is already very sophisticated. Catching people to that to this level of technology will take long time for us, 10 years, 15 years. By then probably there's nothing to harvest, because Intel, you can see there is no more sustainable. Okay, so we have to go beyond CMOS. Not, this is probably would becoming quite complicated. Okay, so this is how the semiconductor chip manufacturing process is. Just for some people who are not from this background, you start from the silicon ingot, then you make the vapor with that, then you pattern this, then you form the transistors, and then you put the connectors, and then you cut in a small chip, and then at the end you get this package, package them, and that's how it comes to your mobile phone. So a lot of process is there before that. Okay. So right now in India, we are focusing mostly on this area. If you hearing a lot of news that semiconductor ecosystem is developing, is mostly on this directions. Like Micron has opened a big, center in Gujarat, which is for the packaging. Okay. So in industry, how this look like, some of you might have worked. So this is how it looked like, a big tool where they load lot of these wafers, like 16, 20 wafers, and that wafers go from one end to other end, and you keep depositing this. So you probably, there is no human intervention, is this all automated, and everything goes by that way. Okay, this is something very cool. I like this image here. The one that you are using, this NAND device, okay, the NAND, which is now 1 TB NAND we can get, is a 1 TB NAND. If you see there, it's a 3D actually integration is there, where we have a 300 layers of the materials, one after another depositing, and you are basically making so many transistors in a vertical directions, and you're connecting them. So this is the line that is coming from here, and it's all connecting to these layers. Very sophisticated things. That is what is being developed. This is done by the mostly Samsung and Western Digital. These are the companies. Okay. So even in semiconductor, if you look semiconductor area, industry, which basically having the component of materials, devices, circuit, and packaging. So not only electronics, you need to know a lot of good material science. You need to know devices, device physics, circuits, and packaging. In fact, in Bay Area, so I worked in Bay Area for a few years. So I found that in Bay Area, if you know very good material science and computer science, you can always get the job. There's so many startups doing new materials. So if you're coming with the new technology, always the materials is the backbone for anything. If you look the energy, if you look the new car, anything you look new thing, you need new materials. You need material scientists who understand materials, how well the materials behaves, and you need novel materials for that purpose. Yeah. Okay, and so this is the other counterpart of this computing system is the storage, which is basically data storage. So beyond the NAND, as I just told about there is one that we typically use for data storage, especially for the cloud purposes, which is called hard disk drive. So whatever data we actually generate, that actually in internet, in Facebook, photo that we upload or whatever we share in the Google Drive, that goes to this hard disk drive that they have in their cloud storage. And I don't know how many of you really know how this works. This is very masterpiece of engineering. So what happened is that this hard disk, if you see, this hard disk has a disk. Okay, that disk has a magnetic materials. Okay, the magnetic grains, and they are well separated grains. There is some way to get those well separated grains. Each grain is around 4 to 5 nanometers in diameters, around that range. And so what happened is that there's you have this read head, which is basically fly on the top of this disk. And you know what is the distance between the disk and the head? Any guess? Random guess? Huh? It's only 2 to 3 nanometers. Okay, and with that it also fly very fast. And probably the people who were using the hard disk drive long back, they probably remember that we supposed to not throw a laptop and a computer, otherwise the hard disk will crash. Because if this disk will touch the head, everything is gone. You can even not retrieve the data basically after, because it's broken. Okay, so this is the beautiful piece of engineering where your disk is flying on the top of that and writing the information on this and also reading the information from this. So the reading is based on something called the magnetic tunnel junction, where the distance, that much small distance is required, because this disk will read the magnetic signal and the magnetic field of this area where you have written the information. Okay. Yeah, so as we all have been hearing about the artificial intelligence, and as many of you are working in these directions, where it is going to bring in next disruptions in all sort of area: transportation, manufacturing, healthcare, education, media, even customer services. Okay, and on the other hand, we are talking about the IoT. This is the nice example here. There they are talking about that in future there will be a smart kitchen where all these appliances will be connected through the net, and you basically have an app, and from your app you put all your recipe, and these all nicely synchronized, and you basically your food will be ready for you. So you can just put your recipe in your app and it will be ready for you. Okay, so what is happening in all these cases? We see that one end, if you look whole this ecosystem, one end we are talking about semiconductor logic systems, which is quite complicated, very advanced. Reaching to there is quite difficult, and there is no further scope of improvement. On the other hand, what we see that AI, IoT, these waves are coming, where we see there is a need of the data. You are moving from one device to the device, and also for IoT, sensors are important. Like you are sensing various things. So how to integrate those sensors with the CMOS. So this is how the ecosystem is coming along, right? And then what you see that for all those things, data is very important. You are transferring data all the time. So today we say that the one who has more data, that company is the rich basically. A lot of companies are becoming rich because they're selling the data, right? The data is the most important. Okay, so today we are generating 2 trillion gigabyte data, and in few years it may be much more than that. Is because we are, whatever data we are creating in the form of the video, photo, audio recording, it's a large varieties of data. We want to keep it. We always have emotional attachment to the data, and most of the time we are sharing it. So when we share the data flow matters, how we're flowing data from one end to other end. And as I'm saying that this IoT devices are going to increase exponentially. So hence the lot of data would be shuffling between the devices in the future. So I can say that the next 10 years would be the decade of memory and storage rather than the processor. Because the processor is quite mature, advanced, there is no further improvement is possible, quite complicated, difficult to make, and not much money you can make. See, the Intel is a dying stage right now. On the other hand, NVIDIA is not making processor, but they are making AI chip. They are booming up. because you're bringing that functionality. So that way we can see the difference. So which direction we have to focus, that's its telling. So basically, if we can handle this AI things, or we can handle a lot of data, there's a lot of opportunity for us. Okay, as I just told that there's an ongoing shift from computer centric to data centric. Also, we need to reduce the energy. So today, even in the data storage centers, the 50% of the energy that we use is just for cooling those systems. And if we don't do any innovations in the future, the next 8 to 10 years, the 30% of the energy that we produce today would be just used by the these IT devices. As today I was talking to Dr. Datta. Yeah, he's not here. So he's using this NVIDIA chip, right? It consumes a lot of energy, really a lot of energy. So they are basically doing the CMOS processor they have, but there are multiple of them in working parallelly. So how much energy you are using with that? Why don't we make the device which is energy efficient and can do the same task which this NVIDIA chip can do right now? Right, so that's another concern. And third is that the memory gap issue that I was telling, that your processor runs much faster, but your memory is not making a pace with that. So there is a gap between those things. How can solve those issues? Okay. Yeah, this is what I was talking about. If you see here, this is our von Neumann architecture look like. In today's the computer scientists can appreciate this better. That at the top of this pyramid we have a CPU which run much faster. At the bottom we have the cloud services. And if you see that the top blue part is the part which is volatile, means when you turn off the power you lose the information. So at the top we have a SRAM. And the DRAM, so dynamic random access memory and static random access memory. So that is typically what we say the RAM. The RAM is the one. So these two are they are volatile. When you turn off the power, you lose the information, and they may run as close to your CPU speed, but they don't store the information. So then whenever you have to get the information, you have to come to this flash drive or local drive, which takes time. And that's why it's created a problem for your computations, and more data you suffer, more and more time it will take. Especially when you talk about the future need, this AI and IoT, that's what it will create a more and more trouble. So that's one part of the things. Other is that we always have some emotional attachment with the data that we create today. We don't want to delete anything. Now what I do is that I keep buying this cloud storage all the time, because my all phone is full with food, but I don't want to delete any photo, anything. Okay, even any random document I have 20 years back, I still want to keep that. This is emotional attachment we have with the data. Right? So how we can store that much of data? Within last 20 years, we have generated so much data. What will happen to after 100 years or 200 years? So we have to find a solution how to save the data in a very efficient way. So there is something called the DNA storage. I don't know how many of you have heard about this. So people are now making a synthetic DNA which you can use for storing the informations. And the calculation says that one cube one cube, a small cube of 1 centimeter, that can actually store all the data that we have created in the world so far, if we make a DNA storage technology. Okay, so the main problem with the DNA storage, I have also worked on that a little bit when I was in Western Digital. We had a collaboration with the Microsoft and a company called the Twist. Okay, so but the main problem with that, you can write the DNA, but reading is very tricky, because it is the small current you can get from that is like nanoampere current, and there's no much difference between one nucleoid to other nucleoids in terms of the current. So it's very difficult to judge that. But yeah, there are some other ways people are figuring out this, and there are other also people are looking other ways to handle this. Yeah. So across the globe, people have been looking various technologies, including spintronics, including ferroelectrics, phase change memory, resistive RAMs, and all sort of things people have been looking to actually bring the alternative devices for this von Neumann architectures. Okay, so you can see that a lot of materials people have been working on, which some of you may appreciate it. Like this is the RAM, basically this is the resistive RAM, ferroelectric RAM, phase change memory, polymer based RAM, spin transfer torque, MRAM, just MRAM, and then metal oxide based resistive RAM, and many other things that people have been working on it. And you can see that there are many companies already developing product based on that. Okay, this is just a benchmark of the various technologies. It's probably not important today. Okay, so how much time I have?
Maybe another 5 minutes.
Okay, okay.
Then we can have more discussion.
Yeah,
on
yeah, sure,
10
sure.
minutes.
Yeah, yeah, sure. So yeah, so I will directly go to here. So I have developed something called the spin filter. Okay, so what is a spin filter? In normal metal, if you apply electric field, the electron, irrespective of their spin polarization, they can basically accelerate toward the positive bias. But we make a filter which only allow, let's say, only up direction spin to pass through it. Okay, so how we actually achieve this kind of things in the real world? When introduce a thin ferromagnetic insulator between the two metallic electrode, and when you put an insulator between the metallic electrode, it act, if it's thin, it will act as a tunnel barrier. It's something called quantum tunneling effect. Okay, so if it's a ferromagnetic insulator or semiconductor, it will have a balanced band conduction band. So there will be a spin split of the band. So there will be two different barrier heights for two different direction of a spin of electron. And with that, with this kind of device, one can actually generate the highly spin polarized current. So we basically pattern, we make the thin films of that, then we pattern by photolithography, focus ion beam nanomachining technique, and then we basically make those spin filter devices. That's how it look like at then this device. So this is a real device image, and yeah, so you can see this is the tunnel junction that we have fabricated, and then that's how we measure. We apply the current from two pad and measure the voltage from other two pad, and this R versus T, resistance versus temperature, this indicates that this has a spin filtering behavior. So because what happens is that when you decrease the temperature, you reduce the thermonic emission, and because of that, what happens is that the resistance weakly increases with the increasing temperature. But when we hit the TC, the Curie temperature of the ferromagnetic insulating material, due to the excess splitting of the conduction band, the barrier height for one direction of the spin will come down. As a result, there will be a preferential tunneling of the up spin or down spin electron, and then the resistance will come down. So this is what you see here. So this lowering of the resistance that demonstrate that this is a spin filter. Okay, I mean, we have done many other work. This is just to one piece of data. Okay. So in ferroelectric memories, also we made something called the ferroelectric tunnel junction, where we introduced the thin ferroelectric material between the two electrode. Okay, and so what happened is that depending upon which way you pull this ferroelectric material, this way or that way, then you may have two different barrier heights. Because what happened is that the bound charges in ferroelectric material, they won't be completely compensated at the interface. And since if you have a electrode with the two different materials, then you will have a two different screen length of the electron. As a result, in for these two different direction of the polarizations, the potential profile will be different. Okay, and that way you can get the large difference between the resistance for the two states. So this is what we have done. We use the zirconia doped hafnium oxide. Some of you might know who is from ferroelectric. People have been now using this hafnium systems, hafnium oxide systems, and so we doped with the zirconia, and we just make 1 nanometer of the film, and we could demonstrate that this film is a ferroelectric. Okay. And then we made the tunnel junction with that, and we could show that it shows the large tunnel electroresistance effect, and that can be useful for memory applications for AI and IoT. Also, we have demonstrated the ultra low energy electric field control of magnetism. So here, what we have done, we use the multiferroic materials. Okay, multiferroic is a bismuth iron oxide. Some of you might know. Okay, BFO, which is basically having a two ferroic order parameters. It's a ferroelectric. Is also magnetic. It's anti-ferromagnetic. Okay, so ferroelectric and anti-ferromagnetic. So if you change the ferroelectric property, you also manipulate this magnetic property. So they are correlated basically. Okay. So what we have done, we put a spin ball, a GMR stack on the top of this, and we could switch this GMR stack just with the electric field. You can see that this is a spin ball, GMR stack, a spin toning device, and we just apply the electric field from -2 to +2 volt, and we can switch the device from low resistance state to high resistance state just with the electric field. So that's demonstrate that we can control the magnetism just with the electric field. Okay, so here we have systematically reduced the thickness and have done more engineering, and we could show that you can actually switch the devices with the 500 millivolt actually, and that is corresponds to the 10 autojoule energy range. Okay, so then we developed this MESO devices, magnetoelectric spin orbit devices, and we published several paper on that. Okay, then as I was saying that telling before some of you that we also developed a technology to pattern the water. Okay, some of you may surprise that why you pattern the water, what is the need of that. So some of you might have seen early work on ionic liquid based gating. So people use the ionic liquid to gate the materials. Okay, so you use as a gate dielectric, And then what happens is the ionic liquid, you have a positive and negative ions, small voltage you apply, you can separate them out. And then you can create the large, electric field at the interface, which is called the nano gap capacitors. Okay. And with that you can create, or electric double layer, which is called. And then with that you can actually change the electronic property of your materials drastically. People have seen that insulator has become superconductor, for example. Or in this science paper, if you see that is normal metal has become ferromagnetic metal with this gating. So this has a huge impact. But what they do, they put big drops of this ionic liquid and then having the hanging gate and demonstrate it. You can publish science nature paper with that because beautiful effect. But how you can actually use this for technology? So if we compare this with the silicon technology, in 1960s, this is how the transistor looked like in the Bell Lab. Now we have come to this stage where we can integrate all of them together and make a IC. What about this idea was, what about the patterning the liquid and make something like that? Okay, so this is what we have developed technique to pattern the water, to deposit water, to pattern it, and to make devices. So it was very crazy project, and you can see that while doing this, we have seen many failures. This is also a lot of failures we have seen, and this is one of the picture that shows that what are the problems one you can see, and the image looks pretty beautiful. So that's why I put it here. Okay, so at the end, with some cryogenic based patterning techniques, we could really pattern the water, and we could put the small droplets of the water, which is 10 micron in diameters and sometime even 1 micron, and we could actually completely encapsulate this between the two electrode. We made a capacitors, we also made a transistors with that, and even the flip-flop circuits, and we could show that these transistors where we have a zinc oxide as a channel, and we can actually switch this on and off state. Okay, and then the idea was that we can actually use them for neuromorphic computing applications. Okay, so what we see that how the overall, if you summarize my today's discussion talk, that what we are now looking for, how we can make the energy efficient computing devices, and at the same time how we solve the memory wall issue. So right now we are on the one domain architecture. People are looking for how we can go from one domain to the near memory computing, even near memory computing to in memory computing or neuromorphic computing. If you go from one end to other end, it become more energy efficient. So that is the direction that we should be more looking forward. Okay, with that, there's no need to even read this all. So with that, I would like to thanks for your attention, and I'm very open for discussion and question. I hope I could say something useful here, and let me know if you have any questions here.
Thank you, Bhagwati Prasad. Let's give a big clap for him. Wonderful lecture. The great job you are doing at Indian Institute of Science, Bangalore. In fact, founder president Dr. Ashok Chauhan ji has been witnessing your presentation right from the beginning. He has been seeing online.
Great, thank you. Thank you, sir.
And so he has sent his greetings, appreciation, and he would like to show this recorded to very large cross section of our Amity universities, other campuses, who may not have been able to attend due to other commitments, like they may be in the lectures or in the practicals or in examination. So we recorded this, and Dr. J. Sodhi has done the recording, and we will put it online to all the people, and then we will show it, and founder himself would like to be again present there. So he has sent a message.
Thank you.
So he appreciated your work and also your willingness to partner with Amity University. So founder president's greetings and blessings to you to continue this mission in a big way. Now it's open to questions. Yes, some of you will have, yes, Basant.
Thank you, Bhagwati. You give the very diversified manner of all these things. Especially you use the filter, spin filter, no? So what is the motivation to produce this spin filter?
Yeah, so a lot of motivation. So I skip the motivation slide because then it takes time. Very good. Thank you for bringing me back to what I want to say. Okay, so here.
Yes.
Before this, yeah, here. So typically, this, as I was saying, this hard disk drive, there's a disk we have, and there is a head. This is the head that fly on the top of that. And at the top, so this read head has something called the magnetic tunnel junction. Okay, so magnetic tunnel junction means you have two magnetic layers. In between, you have a thin non-magnetic insulator layer. Okay, so typically people use MgO for that, for tunneling. Okay, so if these two magnetic layers are parallel, that time the lot of current can pass through. That is called, let's say, 0. And when these two are anti-parallel, less current will pass through. That's called 1. So this MTJ people use for read purpose, reading the information which you write in your hard disk. Now recently people have shown that you can use this for also data storage application. So what you do, so basically what you have to do, there is the two magnetic layer I'm talking about. One is always be constant like that. Other one, which is called the free layer, can shuffle between this state and that state. So depending upon whether it's this way and that way, you can have a 0 and 1. You can write the information, but how you can shuffle, how you can switch this magnet this way to that way. Earlier people are using magnetic field, but that's become very tricky. How you can really focus your magnetic field in such a small area of the device. So now people have learned that you can use the current pass through from this layer become spin polarized. Means current means electron. Electrons are going from this layer. These electrons will have only one spin direction. This is called the spin polarized electron. And then this electron will come and they can transfer the spin angular momentum to the electron on this layer. And that way that can actually change the magnetic direction of this layer either this way and that way, depending upon which way the current is flowing. So basically you generate the highly spin polarized current. You can make this switching of this magnet very easy. Okay, more and more spin polarization it will be there, better it will be. So spin filter you use for that purpose. You basically create a highly spin polarized current. Means electron have only one direction of spin of electron. So when this electron will pass through other materials, ferromagnetic materials, they can basically transfer the spin angular momentum to the electron on that material, and that can change the magnetic state of that material, and that you can use for writing.
Okay, now in continuing of this work, can we use this filter to alter the thermal conductivity of metals? Because you know that the thermal conductivity is measured the part of the motion of the free electrons.
So there are many in spintronics. There are many there are effects like thermal Seebeck effects. There are many spin Seebeck effect. There are many ways one can actually integrate the spin into the thermal conductivity of the materials. Yeah, people do work on that. There's a big magnetocaloric effect is one of that. Yeah, on that direction. Yeah.
Okay,
Thank you,
so I
Dr.
will discuss more detail about this and maybe
Dr. Jain.
Sure.
Professor, I'm V.K. Jain. We were discussing about this semiconductor devices. Only one thing I was also showing to you in the lab that we have done a lot of work before joining here, all the semiconductor devices based on silicon, gallium arsenide, mercury cadmium telluride, all that. So this is all based on our material devices. This is silicon, or suppose we want a UV detector, you made a silicon carbide. Here in MIT, we have changed the scenario. Instead of going to this different materials, which is very difficult, even gallium arsenide we can't do, silicon carbide we can't do, we have changed it that we're growing a silicon nanowires on silicon chip. And the size of the silicon height nanowires on chip is about 5 micron, diameter is 40 to 100 nanometer. And by adjusting the barrier height by making a heterojunction on these nanowires, we can make any device.
Yeah.
My colleague is here, Dr. Avshesh is here. We have made about 20 publications in the new scenario that we can make UV detector, IR detector, your even terra detector.
Sensor application is very useful, not logic. So if we can bring the novel materials for sensing purpose, right, like this kind of detector that you're talking about.
That's why I'm coming to that one.
Yeah.
And my question is, this we have done. This is also very difficult. Very few places this technology is going on. But in MIT, we have optimized this one. Yesterday, we got from SSPL that our sensor for IR, which is the most difficult technology we don't have in India right now, it is responding good in this direction. My question is, can we use this type of nanowires as a memory storage?
People have been using also CNT based systems, even it was in the one of the slide. Yeah. So yeah, here it is. You see that CNT people are using CNT carbon nanotubes. There's some effort is going on that how you can use nanowires for memory applications. In fact, these resistive RAM people do use sometimes these nanocomposites. Nanocomposites also have these channels, small channels, and that basically one can use for memory application. Resistive RAM, yeah. In fact, if you look the resistive RAM, it is basically having nano channels where these cations or the oxygen vacancies, oxygen ions are moving back and forth, right? So yeah, certainly.
Another question, last in your lecture you were saying about the making a junction or sometime in liquids. As I was showing that we have first time done using in a wood or in plant this micro channels, and we have put make some amendments into that, and we have found that in wood micro channels we have first time developed a electronic a diode by our technology. So it has been done, and we have patented. This is known as Woodanix. So
wow.
This one. So this is a new thing. I was telling that even micro channels in wood we can use for this electronic purpose.
Yeah.
Like semiconductor. Thank you.
Yeah, sure. Thank you.
Very nice presentation. In your where you are using the water encapsulated and then you are using the zinc oxide, right, as a channel material. So you are exploring the hydrophobic and hydrophilic properties to that way.
Very good. You got it without telling it.
Anybody else? What about spintronics?
Indeed, it was a wonderful lecture I heard after so many times. And particularly the FERAMs, these work started in late 80s and 90s. But the problem was the ferroelectric material was the dielectric loss. So leakage current was high and material was getting depolarized.
Exactly.
There were other factors too behind this depolarization. So I know that there is advancement of technology also for the fabricating these films. So still, what about the dielectric loss and the boundaries or polycrystalline nature of the film? Whether how it is going to affect the RAM?
Actually, very good question you ask. If you look the perovskite materials, they have a large dielectric constant.
Speak to the mic, please.
Yeah, the perovskite materials has I would like to see it also. That's why. Yeah. So if you see the perovskite materials, they have a large dielectric constant. So when you reduce the dimension, then there's this depolarization happens more. And so to solve that problem, people has used different other materials which has low dielectric constant, but at the same time it has become the thickness has increased, and then you could not get the scalability as you're looking for. But if you look the hafnia, doped hafnia, it has very low dielectric constant compared to other perovskite systems around 20 or something like that. So that way it become quite interesting. And the good thing with the hafnia is that you basically maintain the ferroelectricity ultra thin films. It's other way around in the perovskite. It's become difficult. Here you can maintain that. So that's what is the beauty of this. Only the problem is here is that it need a larger switching voltage. EC is quite high. That is the main problem. So we are doing a lot of work on the happening. If you are interested, let me know. We are figuring out how to reduce the switching voltage. This is one of my interest actually, how to reduce switching voltage. And then we are exploring this whole ferroelectric to anti-ferroelectric phase diagrams, various means, thickness, effect of electrodes, effect of the different cations and moving the oxygens. All those things we are doing in our lab. Yeah.
Actually, hafnium is now replacing the zirconium at the B site in perovskites. Mostly people are now
zirconium doped hafnium oxide I'm talking about.
Yeah.
It's HGO. Yeah.
But I think that's a good thing. We can start with this part actually, hafnium, working on hafnium and then getting this polarization voltage keeping low.
Yeah, that is one of the biggest challenge right now across the globe. So if you go in ferroelectric conference, 70% people are actually working on the doped hafnium system. It's not me.
Yeah.
It's very crowded and a lot of people are, because the main thing is which I did not actually highlight it because I thought probably it will not be the interest for the larger audience here. But now I can say, if you see that this is the beauty of the hafnia, you can grow with the ALD. So atomic layer deposition techniques. With that, you can grow in a three-dimensional way. Okay. Then you can also, silicon integration is well known. That's a big problem. How you can integrate with the CMOS technology. And for as a high K dielectric, people have been using this for a long time. And the other problem is that maintaining the ferroelectricity in ultra thin films, which is actually well known in the zircon doped hafnium oxide, which is how it works actually. in this case. And then scaling is also, it can follow the CMOS scaling, and 3D integration is possible. And also you get the very high polarizations. Only the problem is that the coercivity is higher. Switching board is higher. So that if we can reduce that, then this is going to be winner.
Actually, barium zirconate titanate has proven for the tunability of its dielectric constant, but at the same, and its coercive field is low as compared to the hafnium root material.
Yeah,
but I don't
depolarization problem.
But depolarization is a problem.
That is a problem because the dielectric constant is high.
Yes.
Yeah.
So Shubham,
Okay, thank you.
anything else from your, please.
Sir,
Just pass on the
as
way.
data is increasing by exponential rate, and you have shown the SDDs are used as fundamental units in cloud storage. So, at the capacity of SDDs are limited. So, how you can see in future how you can increase the capacity to store?
So you won't believe that the magnet tape that we used to use 30, 50 years back, again people have again started working on that, how to make a magnetic tape more efficient and high density data storage solutions basically. So though we don't do this work in academia, but industry like Western Digital, IBM, many companies are working and figuring out how to use this tape. That we will not use it, but in a cloud people use it very cheap. Basically they use a FE304, and that's what they use for data storage application. But this is all on the magnetic side. Okay. Other than that, what I'm saying that people are looking for the optical memories, cannot store the data in the form of the optical signals. Also, DNA storage. So those are the other avenues that people have been looking. But this is actually going to be really big problem now. We need to really think about, if we want to keep the data forever, what is the right way and how we can make it more energy efficient and and high density.
Thank you. Last from
Thank you, sir, for giving this very.
Yeah, please go ahead. No, Sarika, wait. He was.
Thank you for this wonderful lecture. Actually, we are quite interested in this PMA, perpendicular magnetic anisotropy, and from the last 2 and 3 years, we are depositing COFB with tantalum and with ruthenium also. In literature, it has been mentioned that PMA will definitely you get, and we tried to measure PMA, but we failed. So you are telling you are having a pulse laser deposition. So have you tried? People were saying that during deposition this stress induced in your films, and this stress will lead to disturb this PMA. It will increase the stress induced anisotropy, and it diminish this perpendicular magnetic anisotropy, and you are having this pulse laser deposition. So does it
no. So okay, so there's a separate lecture on the PMA which is not here today.
Okay.
I presented even Ranchi the last week. Okay, just on the PMA. Whole lecture was about the PMA. Okay, so PMA is, you are talking about cobalt iron boron,
yes,
right?
yes.
So the trick of the trade is that you actually reduce the thickness. So your bulk, basically what you have to do, you have to play with the 4 pi ms.
Yes.
Safe anisotropy. So you have to fight with that. And to fight with that, you have to increase your interfacial anisotropy, right? So for that, you reduce your the ms value. Lower it will be, better it will be, right? So you decrease the thickness. Decrease the thickness around 1 nanometer would be fine. Okay, the cobalt iron boron. Then you annihilate. Then you remove the boron basically. Okay, with annealing.
It gradually goes to the interface.
Exactly. And at the same time, the annealing has to be optimized very well so that you make the nice hybridization between the 2p orbitals and 3d orbitals. And that way you can have this PMA. So that require both things, right thickness of the cobalt iron boron and right annealing temperature and time. So then you will get it.
In this regard, we have deposited this wedge film also, that we will get some particular thickness. But till now we are failing to get this PMA.
You can also use other method, that you said he is doing is cobalt platinum or iron platinum.
Iron platinum.
But you can use a cobalt platinum. So use the cobalt platinum super lattice. Okay, you will get the PMA very easily. We do this quite often in our lab. There you don't need interface. Means interface, but it's more of the spin orbit coupling from the cobalt platinum stack.
Yeah, the last comment from Dr. Sarika. Then actually, you people can, founder president also, watching the program, he is now, each one of you have to submit what you want to do with our Bhagwati Prasad. Because the Indian Institute of Science, the areas which he has opened up, So it's not only for information, but then how we can connect with him, which are the areas you have in mind which you can connect. So please send it to Dr. Vaibhav, my colleague who has coordinated, so that he will compile it and then send it to founder president. Your views, what you like to do in this big mission which Dr. Bhagwati Prasad has presented today. Yes, Sarika, then
Hello.
we'll conclude.
Yeah, the presentation was very nice. Actually, some of our colleagues, like those who are from IT department, may not be able to relate much of it. But still, which I know, like IoT still can be connected with these devices. But the role of AI, how is it working with semiconductors and everything? One particular aspect I know, like we can optimize the performance of these devices because this semiconductor is basically the just the arrangement of these capacitors and transistors. So I think the optimization process of AI this could work, and how other pillars of AI could enhance the productivity or the operations and the efficiency of all these devices. Can you bring a little bit shadow on these aspects?
That is called the AI for AI development, right?
Yeah.
So certainly, I mean, now if people are using AI and machine learning a lot on the material science actually to figuring out the new materials. There are a lot of research paper has been published recently. At the end, what you see that the permutation combination of all sort of materials in the periodic table, am I right? And right recipe for them, right temperature, like right processing parameters. It is impossible for the human being to do everything and try and then figure it out. So I think AI ML has come at a very right time. I would say that that's why the Nobel Prize was given this year. Nobel Prize in Physics and Chemistry was given in the AI, which is very unlikely because they are not basically fundamental physics. It's more of the tool techniques. But they with the help of that they could have developed something novel. So I would say AI ML has a huge role, and it's going to change, transform the world the way we perceive the world today. Actually, it will make everyone's life much easier. I do see that there's a huge difference is going to come, and I learned that from the someone from here that the president from your president has given the mandate that to Datta Sarji that everyone in the institute need to learn AI.
Yes.
That's a really
every student, every faculty, we want to make them.
I think it's not
AI
it's not a
savvy.
subject. It is going to become tool. It is going to become tool to live our life.
Absolutely,
Tool
it's a
to
part
do
of our
our-
life.
Yeah,
Become part
that's
of
how
our
it is
life.
going to become. And eventually, at the end, what is AI is you know much better than me. But for me, it's basically you are using some tools, some softwares, which can help us to synthesize tons of information in a very short span of time and give me the final solutions, which I cannot do by myself, which is beyond the capability of the human being. And that's why we need the machine. So machine will help us to synthesize tons of data and give me the some right form of information. So certainly it's very useful. Yeah.
Just give this.
We will work for data storage tools and all. For this, nowadays we are working on Hadoop is there for data processing and all, right? So we will work together for storage part. As a IT person, we will work on it. We'll let you know.
Bhagwati, come.
Yeah, okay. I'm done.
What a fantastic lecture it was. Let's give yet another big clap. And with so much passion and the dedication you have given this lecture, Bhagwati, and also this your depth of knowledge, understanding the way you dealt with that complicated topic, and the presented the challenge, what is available today in a very simple way. This all speaks volumes of your talents, capability. So, on behalf of Founder President, Chancellor, and all of us in MIT, we like to express our gratitudes to you. But more importantly, that your lecture has opened up many thought process from all our colleagues who have attended both here physically and also online. So we would be asking from every one of them that what you intend to do with our Dr. Bhagwati Prasad in this major initiative which they are looking at Indian Institute of Science, Rice University, and also Amity University. And we are all partners. All three of us are very strong partners. So something exciting should happen. It's not that just incremental in, as he said, disruptive. What is the disruptive thing we want to do together? So please think, pen down the concept in even if it is half page, 1 page, that this is what we would like to do. Some of the comments which you made, and then we will first scrutinize, and we'll also send it to founder president for his guidance. After that, we will share with him, and we'll show it to chancellor, because chancellor is the one who organized this. He asked me to organize this, so we will be sending a report to him as well. So thank you, Bhagwati, and thank you for all of you to come and then interact. But this is only the beginning. Now, as founder says, पार्टी शुरू होता है अभी अभी पार्टी शुरू हो गया. So now you need to see what all we are going to do together. I'll be eagerly waiting for your report. So take at least by Monday evening, because you still have tomorrow, Saturday, Sunday, Monday. If you can just send me that small note that this is the area, then we will build. We will call him on Zoom meetings and then try to see where we converge together for collaboration. So with this, once again, thank you, Dr. Bhagwati. I will also convey Dr. Chancellor, Dr. Abdul greetings to you. We have a small memento on behalf of Amity. Please accept. Let's give a quick clap to Vaibhav. Vaibhav organized this whole event, and he himself is a material scientist. He works on ferromagnetic, and also he works on special materials. So he's the right person to handle this, and he will collate all your thoughts. Thank you so much. Thanks. We will have the SSPL project review meeting now. Arup, so other people have come? Okay. Yes. Yes.